This is the movement of water through these channels of polycarbonate sheets, and below is a link to one of the examples of making this cheap solar collector. Typically, such sheets are used to heat pool water when solar radiation is absorbed by the dark surface and therefore heats the pool water which moves through those channels. But the pool heating occurs in the summer, and our solar collectors are inactive during the winter months, and let's analyze how they can completely heat a house in winter. As it turns out, a house needs to have about 20 square meters of the polycarbonate solar collectors, which will cost several $100s and connect a similar canopy or walls of a gazebo, pool or greenhouse. It should not be water, but an antifreeze liquid that constantly circulates along this path through this heat pump, which heats our house completely 100%. In other words, the solar collector continuously transfers thermal energy to the heat pump 24 hours a day, during sunny hours, cloudy hours, and at night. The bright sun will hit the antifreeze, whose temperature will be approximately 10 degrees higher than the ambient temperature, and this formula allows you to calculate that temperature difference and this antifreeze heating power. The formula corresponds to this line on these well-known graphs from Wikipedia, where we see that our solar heater performs radically worse than this line of such well-known solar pool heaters. We also see that the heating temperature of the antifreeze will always be less than 20 degrees Celsius in the winter months, and therefore this heat pump is our only option for heating the house. In general, this line corresponds to a wide class of solar heaters, which includes not only our polycarbonate collectors but also similar sheets or the same pool heaters if they hang like this without any thermal insulation. Experts will call this class by this term, and this table compares its energy parameters with the classes of this graph. Sunny weather gives approximately this flux of solar radiation, but the radiation flux from a cloudy sky is approximately 10 times less, and the calculations use the same formula with a modification here. This is the same formula, but for the case when the average temperature of the antifreeze is equal to the ambient temperature, and in this case almost all the energy of photons from the cloudy sky is converted into heating of the antifreeze and goes to the heat pump. The night air will continually heat this antifreeze because the average temperature of the antifreeze will be about 2 degrees colder than the ambient temperature. The formula is the same, but this solar flux is zero, and therefore the formula becomes like this. This is a comparison of our case with this traditional heat pump which takes thermal energy from the ground, and with this traditional air source heat pump. We see that our heat pump occupies an intermediate position between these well-known goods, the purchase and installation of which in private homes has a global turnover of almost $90 billion annually. On the one hand, our heat pump is radically cheaper than these ground source heat pumps, which are forced to build similar very expensive systems for extracting thermal energy from the ground. On the other hand, here we see that our heat pump consumes less electricity than such traditional heat pumps. This is because the average temperature of the antifreeze here at the inlet to our heat pump is approximately 5 degrees Celsius higher than the average ambient air temperature at the inlet of a traditional heat pump. Also, the electricity consumption of this traditional fan is several times greater than this antifreeze pump, and the transfer of heat from the liquid is radically more efficient than traditional transfer of heat from air. In addition, the lack of power of traditional heat pumps in cold weather forces them to use electric heaters more often, because the coldest days are usually sunny when the sun gives our heat pump a lot of energy. This is the power of the heat transfer from our polycarbonate sheets to the heat pump during the 24 hours, which begin with a perfectly sunny day from this sunrise to this sunset. We see that here in the evening the transfer power is radically greater than at night due to the gradual decrease in ambient temperature from evening to morning. Here the power is maximum due to the high temperature of the antifreeze, and this large amount of heat is accumulated in this large mass of concrete of the home heating system, and this heat will go into the rooms in the evening and at night. This is the same, but this day is not sunny but cloudy. This daytime heat transfer power is greater than at night because the ambient air temperature is slightly higher during these hours, and also here the solar energy from the cloudy sky slightly heats up the antifreeze inside our sheets.